Good afternoon, everybody. It's 12 o'clock, so we're going to go ahead and get started. Just to mention before we get started, labs are ongoing this week. So the first lab of the week was this morning at 9. If that was your lab section and you didn't go to it, you should get in touch with your lab instructor as soon as possible because you have missed a session if today was your period and you didn't go. And if you miss a session, kind of the default is to get a 0, so you'll have to ask Dr. Lee if he can help you out if you did miss today. Assignment 1 is open. We started covering that material. I encourage you to work on it as we go through just to make sure you're doing okay. Before we get started for today, are there any questions about anything? Okay, so we're good to get started. Last day we started our topic of waves. We talked about what a traveling wave was. We looked at transverse wave and longitudinal waves. We described a wave at any one single position and at any one single time, and then we started to put those two concepts together to get an expression for the height of the wave as a function of position and time together. So that was what we got to, and that's what we're going to finish for today. And then we'll move on to some other stuff. So this is our slide from last time. This is how far we got. Just as a refresher, we started by drawing some generic wave. We said that it was at time t equals 0. We said that the wave was moving to the right with wave speed v. And we know that this wave is a sinusoid. So the height of the string as a function of position at time t equals 0 is the amplitude times the cosine times our wave number k, that's 2 pi over lambda, times the position plus a phase constant. So we wrote down the expression for y as a function of x when t equals 0. Then we said, well, what if t is not equal to 0? What if we let the wave move? It's going to slide to the right a little bit. So down here on this picture, we've got our t equals 0 wave. We've also let it move to the right a little bit, so that's at time t. What happens is that this new wave, this pink one, moved over a little bit. The distance it moved was speed times time. And we're trying to write an expression for this pink wave right here, because this is at any generic space at any generic time. What we recognize is that if this is our point x, the height of the wave at this point is exactly the same as the height of the t equals 0 wave, but it's a distance of dt behind. So y of x is the same as y of x minus dt for the t equals 0 wave. That was what we got to last time. So we said this generic pink wave is equal to this wave, that little bit of distance behind. So we wrote down this function at this little bit of distance behind. So that's where we got to. We're going to pick up here with our algebra now. So let's write out what we had. We've got a times cosine 2 pi over lambda times x. And then our distributive property minus 2 pi divided by lambda times v times t, and then we've still got our phi. Okay, so that's just a little bit of algebra there. My pen slipped a little bit. This very funny looking thing is supposed to be pi. Sorry about that. Okay, so 2 pi over lambda times vt. This first 2 pi over lambda, that's our wave number k. That was something new we defined last time. That's how a wave repeats in space. So this term is going to be k times x. For this term, we can do a little bit of work right here. If we look at this bit, v divided by lambda, we should be able to recognize v divided by lambda because we know v equals f times lambda. That means v divided by lambda equals f. So then this term is really 2 pi f. So 2 pi times v over lambda equals 2 pi f. 2 pi f, that's our angular frequency omega. So this whole bit right here is actually omega. Okay, let's put all that together so that it looks a little bit nice. So the height of a wave at a horizontal position x and time t moving with speed v is given by this equation. y of x and t is equal to the amplitude times cosine kx minus omega t plus our wave constant, our phase constant phi. So that's our equation for a wave, a sinusoidal wave that moves to the right. Okay. So we can do, I'm not going to, I suggest maybe you try this for homework. We can repeat this process for a wave that moves to the left. So instead of the wave moving to the right a little bit, we could ask what would happen if the wave moved to the left a little bit. If you follow the same process, what you should find is y of x and t equals a times cosine kx plus omega t plus phi. That would be for a wave traveling to the left. And I'm going to suggest you try that as a homework exercise. Okay, so if you can do that left traveling one, it means you kind of got a good handle on our derivation that we did for the right traveling one. Okay, questions? This kind of derivation is absolutely fair game for the test. Anything we do in class could show up on the test. Sometimes people like to ask if you could see this again. So yeah, this can definitely come back. Okay, let's do a conceptual example before we move into some number examples. Yeah?
For omega, it's 2 pi v by lambda, is it?
Yeah, so 2 pi times v divided by lambda is the same as 2 pi times f, because v over lambda is equal to f.
Isn't 1 over t? Oh, v over lambda.
Yeah. Okay, so our conceptual example. A wave on a string is traveling to the right. So here's our wave speed v going to the right. At this instant, so we've taken a snapshot or we hit pause on our simulation. So at this very instant, the piece of string marked with a dot, so this bit right here, is it moving up, moving down, moving right, moving left, or is it zero, not moving at all? So I'm going to give you a minute to think about it. Please feel free to discuss with a neighbor what you think the answer is. And at the end of a minute, I'm going to ask everybody to commit to the answer. You're not going to have to say it out loud if you don't want to. I will invite you to. So you've got about a minute to think about it. And feel free to discuss if you want to.
Excuse me. For the direction of the omega, do we have to take one side and then the other side becomes minus? Or
What do
is
you
it
mean?
just the formula?
Yeah, it's just v over lambda is f, and 2 pi f is omega.
Direction doesn't mean minus or plus, so it won't be like a vector.
No, omega is not a vector. It's just a magnitude. Yeah. Okay, so I'm going to say that was enough time to think about it. Now, this part is critical. You have to write down what your answer is. So everybody with your paper out in front of you, write down what your answer is. If you don't have a sheet of paper in front of you, commit to it in your head. You can't say, I think it's A, but it could be B, and also maybe it's D. You can't do that. You got to commit. One answer and one answer only. Okay, so now that we've all committed, does anybody want to share? Yeah. So my first answer we got was very confident up. Anybody agree with up? A little bit of agreement there. Anybody disagree? Okay, the disagreements, so what do you think the direction is?
I'm going to say E, not so much on physical intuition, unfortunately not because of physical intuition, but just because the Y direction should not be exclusive to the X direction at any point if it's not at rest.
So you're saying it's not moving at all. Any agreement with E? Okay, some agreement with E. So anybody who is not saying up or still, any more disagreement? So it looks like the two answers on the table are up and still. Okay, so let's figure out the answer. So we had probably a third of the class kind of committed to an answer out loud. That's fine. I think everybody committed on paper. And maybe some other people thought some other things and they just don't want to say, which is also fine. But I think the idea that kind of two groups disagreed is a good way to show that these problems aren't always that simple. They're not really trivial to figure out. So sometimes it just takes some thought to get these things right. So I'm going to suggest right off the top, there's probably two ways we can try and sort this out. First is if this is a homework question, then you'll have access to your computer and you can do a simulation. So I've set up one of these PhET simulations. I've got a wave which will move to the right. I've set it up so it looks like our example, and I've paused so one of the green dots is on the line. So what I'm asking is when we take the next step forward in time, does the dot go up, down, left, right, or stay still? So I'm going to push this button, which is going to step it forward. It goes up. Okay, so that's what it's doing in time, is going up. If this were a test question, you wouldn't have access to a simulation. It's okay, you can still figure it out. So let's see if we can look at what the motion is doing in time. The wave is moving to the right. So before it got to here, it was a little bit to the left. Okay, so I'm going to label this pink wave before. So my handwriting's a little bit small, I'm just going to zoom in. So my dot on my string before, this position was down right here. And then after, it moves a little bit more to the right. Now this spot on the string is right here. So my dot goes from here to here to here. It definitely moves up. Okay, makes sense? Okay, so for all of you who said up, you can give yourself a little star next to your answer. You got it right, good job. But lots of these questions, and I do try to come back to these on tests, these sort of conceptual ideas, they're really important, but again, they're not trivial. You have to think about them a little bit, and you have to think, what do I know about waves and how they move? Questions? No? Okay. So next, let's go through a fairly typical example. So in this example, I've got that the vertical position of a traveling wave, so that's y, the height of the string, is described by the equation. So the height of the string is a function of position and time, is 0.75 centimeters times cosine 6.28. I wrote this, I'm going to say that this is not the best notation. I wrote it this way a little bit on purpose because some textbooks do write it like this. If this were a test question or an assignment question, I would write this with the units included, 6.28 meters to the minus 1 and 314 seconds to the minus 1. Okay, so typically I would write it that way, but once in a while you'll come across problems that don't include units. You're supposed to, in that case, figure out that the units are meters to the minus 1 and 314 seconds to the minus 1. So that might be in some of your textbooks. So that was why I wrote it that way. Okay, then we've got a list of questions. Is it moving left or right? What's the amplitude, wavelength, frequency? How fast is it going? And then we want some other ones about the wave maximum and minimum. So the first thing typically we're going to do when you get an equation with numbers like this, the best, well, in my opinion, the best first way to start is just write down your equation with symbols, because you're going to use a comparison to give you lots of information. So this equation in symbols would be y of x and t is the amplitude times cosine kx, that's a minus, so that'll stay a minus, omega t plus phi. So writing it down this way puts us in good shape to figure out the amplitude, wave number, angular frequency, and phase constant. That's why we write it down in symbols next to the numbers. Okay, now let's get into the question. Is the wave moving left or right?
Right.
Okay, got a very confident right. Who agrees with right? Yep, right is absolutely correct because we have the form kx minus omega t. On most test questions, you do have to support your answer. So if this was part A of a test question, it wouldn't be enough to say to the right. It's to the right because it has the form of kx minus omega t. If it had the form kx plus omega t, then it would be a left-moving wave. So you should always support your answers. Part B, what's the amplitude of the wave?
0.75.
That's where our comparison comes in. A is what comes before the cosine, 0.75 centimeters. Wavelength and frequency. These are reasonably straightforward, but we can't get this from a straight up comparison. So part C, we'd like to have the wavelength. We have to think about what variable is connected to the wavelength. That's the wave number k. We know that our wave number k is 2 pi divided by lambda. That means our wavelength lambda is 2 pi divided by k. So 2 pi divided by 6.28 meters to the minus 1 gives us a wavelength of 1 meter. So there's our wavelength. Next, we want the frequency. What is f? Frequency f is related to our angular frequency omega. We know omega is 2 pi times f. That means f is omega divided by 2 pi. 314 seconds to the minus 1 divided by 2 pi will give us 50 hertz. Important here, omega is not negative. Omega is always a positive number. You can't have a negative angular frequency or a negative frequency, right? You don't have minus 10 oscillations per second. That doesn't make any sense. Okay, so omega is always positive. Part D, what is the speed of this wave? We've got two choices for doing our wave speed. We know that v is equal to f times lambda. So we just found f, we just found lambda. Or we know that v is omega divided by k. So omega is 314 seconds to the minus 1. K is 6.28 meters to the minus 1. So our wave speed v is 50 meters per second. Okay, questions to hear? Yeah?
Yeah, so the amplitude was given to us in centimeter, and how can we be sure that the 6.28 is in meters inverse and
Okay, so that's a really good question. And the question was, since amplitude is given in centimeters, how do you know 6.28 is in meters? When books write it this way, they just mean meters, which is why when I write it, when I put it on a test and assignment, I'm always going to put the units in there. Yeah, that's a good question, right? Which is why I don't think books should write it that way, they just do.
I also have a second question. Is it a given that the wave equation will always be in cosine?
That's such a good question. A sinusoid, sine and cosine are essentially the same function. They both go up and down, right? So one could argue that it's just as valid to use a sine function as a cosine function, and I would agree with the physics behind that statement. That said, your textbook uses cosine, so I will use cosine. Yes. Okay, so we've got our straightforward questions done. Now let's come to something that might be a little bit more difficult. At the position x equals 0, so that's right here at our piston, at what times is the wave at a maximum? And by at a maximum, we mean at what time is the piston at the crest of the wave, or is y equal to the amplitude? So that's what the question is asking. One can certainly do this question just from using the equations, and I'm going to solve it using the equations, but it can help to have the graph in front of you as well. So what I did, because I make a lot of graphs on Excel, was I used Excel to plot this graph. You can also plot this by hand. It wouldn't be very difficult. So my question, part E, is talking about at the position x equals 0. So I took my equation for y. I put in x equals 0, so that term was gone. I took this equation, I put it in Excel, and I got a plot for what that wave looks like where x is equal to 0. So this is something I did to help visualize the problem. You can do it too. If you skip this step, it's fine, but it can help you understand. So this is our graph, our y value, when x is equal to 0 as a function of time. The question is, where is y equal to a maximum, or where is y equal to a? Or when, I should say. So if we look at our graph, we know that this is an answer, this is an answer, this is an answer, and this is an answer. This will be our first time T1, that'll be the second one T2, that'll be T3, and T4, and so on. So we're good with the idea? The other thing about plotting the graph, if you can do it, is it gives you a ballpark value of what the answers are. You can check and see if you're right from your calculations. So let's get into the math of it. So we know x is equal to 0. We know y is equal to a. So we'll write down our equation. Y at x equals 0 and time equals t is a times cosine wave number k times 0 minus omega times t plus phi. If you're a numbers kind of person, you're probably going to write down this equation with all numbers. If you do it that way, that's fine. I find I get tangled up writing numbers down. I put them down backwards half the time, so I'm going to stick with symbols for a little while. But if you did numbers, you'd still solve this just fine. So right off the bat, k times 0, that's just 0. Our y value is the amplitude. So a is equal to a times cosine minus omega t plus phi. Are we good to hear? What we're trying to solve for is what is our t value, what is our time. T is buried in the cosine, so we've got to get rid of the cosine. The first thing we do is divide both sides by the amplitude. So 1 equals cosine minus omega t plus phi. To get to our t, we've got to get rid of the cosine. The way we get rid of the cosine is to do the inverse cosine of both sides. So the inverse cosine of a cosine leaves us with the argument. And that's going to be the inverse cosine of that. Are we still okay to hear? Okay. So omega is fine, we know that value. Phi is fine, we know that value. The next thing we have to deal with is what is the inverse cosine of 1? So that question is more or less saying, for what angle do we hit the cosine button and we get 1 for our answer? 0. Some people are going to know that off the top of their heads. Some people are going to use their calculator. Either way, it's fine. The right answer is the right answer, however you get it. If you use your calculator, you've got to remember to put your calculator in radians mode. That's definitely important enough to write down. So when we use our calculator, It's gonna be in radians mode. You're gonna hit inverse cosine of 1, and your calculator is gonna tell you 0. Okay, so that's what your calculator is gonna tell you. In the back of your mind, you're probably wondering, is that the only angle? Right? And the answer is no, it's not the only angle. 2 pi is also an answer, so is 4 pi, so is 6 pi, those are all values. Okay, so we're thinking that when we do inverse cosines, there's always more than one answer. Okay, let's keep going with this work. So we've got minus omega t plus phi equals 0. T is equal to minus phi divided by minus omega. Our phase constant phi was pi over 4 radians. Our omega was 314 radians per second. That gives us a value of t of 0.00250 seconds. When we ask for at what time is it at the amplitude, we typically, I guess you could argue this, we typically mean positive times. Like, you could get into an argument about, well, don't the negative time count? Like, yeah, it kind of does, but we mean the positive ones. Okay, so we're going to answer with positive times. This is our very first time. So this is our T1. I'm going to put a 1 on here next. But we know that's not the only answer. So we want to write down all of our answers. If this is T1, what's an easy way to find T2? Double it? I like how you're thinking, but we're not at the right answer yet. Does anybody have another idea?
Add 2 pi.
Add 2 pi, you're kind of getting somewhere too. If we did inverse cosine of 1 and got 2 pi here and did our math again here, we'd get our next answer. So we could do it that way. Any other ideas?
Time period.
Someone said the period.
Can reverse to
Can do what?
the cosine reverse to or not? I got one.
Still working with the cosine.
No.
One more answer.
Plus 2 pi times k.
Plus 2 pi times k. K doesn't come in here because we did k times 0.
Or the omega.
Yeah. So yeah, our answer here, so kind of 2 ways to go at it. We can keep redoing this equation. The inverse cosine is 0. The inverse cosine is 2 pi. The inverse cosine is 4 pi. The inverse cosine is 6 pi. We can do that all day until our fingers fall off. Or we can add another period. That's another valid way to do it because we know it repeats every period. So lots of times, there's more than one way to answer a question. It's good to know that as well. And as long as you have valid physics, I am going to mark it correct. So our second time is T1 plus a period. We found the frequency was 50 hertz. So finding the period is not too difficult. That's 1 over the frequency, 0.02 seconds. So our next time, T2, is 0.0225 seconds. Our next time, T3, we're going to add on another period. So T3 would be T2 plus another period, 0.0425 seconds, blah, blah, blah. Then to finish, we want to write our answer so it looks nice. The way we write our answer, I don't have very much room down here, so I'm just going to come off onto the side. All of our times, Tn, is going to be our first time, 0.00250 seconds, plus n times the period, where n is 0, 1, 2, ... Or for t, you could put in your time 0.02 seconds. Okay, so this gives us all times, so the entire set of times up to infinity, where that piston is at the amplitude. Okay, any questions? Yeah?
How did you get the value for the phase constant?
Oh, I just read it from the equation. So right here in the equation, I had plus pi over 4 here, lined up with the phase constant. Yeah, good question. Okay, so the final part of this question, part F, is similar, not the same. at time t equals 0, what are the positions, what are the x values of the first maximum, y equals a, and first minimum, y equals negative a. So let's go through that one as well. So once again, for me, it helps to draw a graph. So I took my equation, I put in t equals 0 here, and I did a plot of y as a function of x. I did that on Excel. You can also draw it by hand if you wish. And the point is just to give you an idea of where your answer is going. So what we want to know is t equals 0. Where is y equals a the first time? And where is y equals negative a? Also the first one. When we talk about the first position, it means the first position after 0. Okay? So it's important to recognize that this means a positive answer. So the answers we're after here are for the first minimum, it's going to be down here for this x. First maximum, it's going to be up here for this x value. Okay, so these are the answers we're looking for because these are the first ones that happen after x equals 0. So let's write down our equation. Y at some position x at time t equals 0 is a times cosine k times x minus omega times 0 plus our phase constant phi. This omega times 0 business, that's gone. Let's do our maximum first. So for the maximum, a equals a times cosine kx plus phi. Divide both sides by a. 1 is equal to cosine kx plus phi. You've got to take the inverse cosines of both sides. So kx plus phi equals the inverse cosine of 1. We already established that that's going to be 0. Okay, I went through that bit really quickly because we did it on the last slide. I'm just assuming that that part's okay. Okay, we want to solve for x here, if everybody's good with those algebraic steps. X is going to be minus phi divided by k. Our phase constant phi was pi over 4 radians. K, our wave number was 6.28 radians per meter. Don't drop your negative sign, and we get negative 0.125 meters. So when we go with what the calculator told us, we get a negative answer. If this were a test question and you did this on the test, you would get some points here, but you wouldn't get full points, right? You've gone through the process nicely and you've done everything well, but the answer we want is the first one after 0. The answer we got from Trust in our calculator was the first one closest to 0 on the negative sign. Okay, if this is the one we want, anybody have any ideas on what we're going to do here? Yeah. I'm going to say yes, but let's add the wavelength, right? Because we have a graph as a function of position. That means this one repeats with wavelength. So our amplitudes are a wavelength apart. So a fast way to get to our answer is going to be to add on the wavelength. Another way, if you wanted to go back to the cosine business, inverse cosine of 1 could also be 2 pi. So if you wanted to go the math route, that would work as well. That would get you a positive x value. Yep. So let's try adding on the wavelength and see what we get. So my x for my first maximum is going to be negative 0.125 meters. Add on my wavelength, which was 1 meter. Plus 1.00 meters. And I get 0.875 meters, which looks like what it is on the graph. Okay, so there's my first maximum. Okay, ideas for finding the minimum x.
Add half lambda.
Okay, so one thing we can definitely do is recognize that between a crest and a trough, it is separated by lambda over 2. That's going to be our quick way to do it. What if we wanted to take our time and go through the equations? What could we try there?
Why is negative
Okay, if we wanted to go with the equations for the minimum, and I won't solve this, but I'll write it down just in case anybody prefers it this way. We would know that for a minimum, minus a is a times cosine kx plus 5. Right, so that would be a valid strategy as well, and you could solve for your x. So we can also just add on half of our wavelength. So x min equals negative 0.125 meters plus 1/2 of a wavelength, 1 meter over 2, to get 0.375 meters. So a lot of solving these problems will be often just tied to how you think about math. You know, there are different ways to follow the math to get to the answer. So when I can, I'll try and prevent you kind of some alternate strategies in class. Okay, any questions? Yeah.
What happened to the negative and the first one where it says kx minus omega 0?
So right here, our next line in the equation would be kx minus 0 plus 5. Right, so minus 0, you can just scratch that out, because it's just 0, right?
Oh, yeah.
If we subtract 0, nothing changes.
For the equation where you write 1 equals cosine kx plus, would you be able to just write 0.5 equals cosine to be able to get, or am I like way up?
Oh, from here?
Yeah,
Where would the 0.5
or to get the minimum,
come
sorry.
from? For the minimum is when y is equal to negative a.
Yes,
So down here, y equals minus a, which is what we wrote in this equation.
yeah,
It wouldn't be a 0.5, because that would be at half the amplitude. That's like right here.
yes, okay.
Okay. All right. Excellent. I love when people are thinking. Yep.
Yeah. What if y is not equal to 1, 2? So what do we do?
Okay, so that's a good question. What if y is not the amplitude? If I had asked this question, find the position where y is equal to 1/2 the amplitude, you would put in a over 2 right here and carry on, right? So then when you get a digit right here, this is when we'd have 0.5 is cosine kx plus 5. And right here you get inverse cosine of 0.5. That one gets a little bit more tangly with the algebra, and we are coming to a problem like that.
Right, okay. So that'd actually be for a quarter of that.
Yeah, okay, so
Gotcha.
we'll do loads of questions when we get there, for sure. Okay, so next coming up in the slides is some homework questions. I recognize that this process is at least a little bit new. So I think I've got a video made to solve this one. For some of them, I'll do a video solution for you, and that might help you get through it as well. Okay. So we've got another little topic to come from before we get to our tanglier examples. So we said before that when we have a wave, bits of the string aren't going kind of from one spot to another. Bits of the string are going up and down. So we're going to talk about the velocity of the bits of string itself. So when we have a wave or a disturbance, it's going to travel with a wave speed v. So this wave is moving to the right. That wave speed v is f times lambda, or omega over k, and that's a constant speed. In the real world, lots of these waves do move with changing speeds. Those are really complicated to analyze. Those are not the waves we're looking at, but certainly they do exist. Okay, so our disturbance is traveling with this wave speed. We know that that the wave is traveling because the string is going up and down. When our source goes up and down with simple harmonic motion, that's when we have our sinusoidal wave. And every bit of the string also goes up and down in simple harmonic motion. Okay, so this is what we established for our sinusoidal waves. Every single element is moving up and down with simple harmonic motion because the source is moving up and down with simple harmonic motion, and it pulls all the bits of string with it. So this little bit of string has a velocity, and we can find that velocity. That velocity is called the transverse velocity. So every element has what we call transverse velocity. And to differentiate that from our wave speed v, we call this v, and we put a little y on as a subscript. So make sure you know the difference between a wave speed and a transverse velocity. The wave speed is how the disturbance travels, how the bump travels. The transverse velocity is how the string goes up and down. And then this transverse velocity is going up and down with simple harmonic motion. This velocity is not constant. Sometimes it moves up, sometimes it moves down. It's changing speed, so it's not a constant velocity. So our next task is going to be to find an expression for the transverse velocity. Because we know the equation for the height of the string, all we have to do to get the velocity is going to be to take the derivative. So that's where we're going next. Okay, so here's where I've just written down the definition of transverse velocity again. The equation for a part of the string, for a part of the medium, so the height of the string at any x at any t, this is going to be, our analysis is going to be for a string moving to the right, a wave moving to the right. If we want to find the velocity, we have to do the derivative of position. So our transverse velocity is the derivative of position with respect to time. So this is a notation that may be new to some people. This is called a partial derivative. It's a curly d. I think in math speak they call that a die. So this would be die y, die t. That feels a little ominous to me, so usually I'll just say partial derivative. How many people know partial derivatives already? Okay, some. Okay, so some people know partial derivatives, some people don't. A partial derivative is not a big deal. It just means we want to know the change with respect to time, which means we don't care how it changes with respect to anything else. We treat everything else as constant. Time is the only variable we care about the change with. Okay, so this is a partial derivative. That means everything except t is constant. So let's get into solving this. Our transverse velocity as a function of position and time is going to be the partial derivative with respect to time of our equation for position. A times cosine kx minus omega t plus phi. When we did the derivative, when I was doing the review of simple harmonic motion, I didn't go through the steps of that derivative. I am going to go through the steps of this derivative. So if you're really practiced with derivatives, this next minute or two might be kind of boring. Feel free to zone out. So when we take a derivative, the first thing we can do is take our constants outside. So that a can come out front of the derivative symbol. So a times the partial derivative with respect to time times cosine kx minus omega t plus phi. Okay, so your constant comes out front. The next bit we have to take the derivative of is the cosine function, because everything else is trapped inside the cosine there. The derivative cosine, you might remember this off the top of your head, you might look it up in a book. On a test, I would give you this derivative. The derivative of cosine is negative sine. So I've got a times negative sine with the same argument. And then to finish, we have to apply the chain rule, which says we also have to do the derivative of the argument itself. So here's my negative sign, and now I have to multiply by the partial derivative with respect to time of this entire argument. And my brackets are all good. Are we okay to this step? Questions? All right, so the A bit's okay, the sine bit's okay. Let's deal with this bit next. So for this bit, it's taking the derivative of 3 terms. Remember, everything except t is constant. So if I do the derivative of k times x, I'm taking k as constant, x is constant. The derivative of a constant is 0. So the derivative of k times x is 0. The derivative of negative omega times t is minus omega. That's your power law. And the derivative of phi is a constant. Your phase constant is just a number. Derivative of a constant is 0. So altogether, that's just minus omega. So this gives us a, I'm going to take this minus omega from back here, pull it to the front. And I've got minus omega times the minus in front of my sign. That's going to give us a positive. A times omega times sine kx minus omega t plus phi. Okay, any questions about those steps? Yeah?
So for the partial derivatives, we just treat every variable outside of the specified domain as a constant?
Yes, exactly. Yeah, that's how you do a partial derivative. When we did the V equation in simple harmonic motion, we stopped to ask what the maximum velocity was. We can do that here as well. If we want to get V maximum, we recognize that sine can go between +1 and -1. So if sine kx minus omega t plus phi is equal to +1, then our velocity Vy is equal to a times omega, and that's going to be the maximum value. Okay, so in simple harmonic motion, your maximum velocity was a omega. That's true too for your transverse velocity, which makes sense because that's moving with simple harmonic motion. It should have the same maximum. We're about 2 minutes short of class being over, but this is kind of a nice place to quit. So I'm going to stop here. Today I have to run to another class in a different building, so I don't have time for questions right after class today. But if anybody has questions, please come see me in my office. I've got office hours this afternoon.